Hi there, welcome back to the formulaic approach. In this video, we are going to be looking at charge distribution on a surface. And our surface in this case is going to be a disk, all right? A spherical or circular disk, okay? So, and the question says that, this one such exam question you might see, that says that a flat circular disk of radius r carries a uniform surface density sigma, which is with the unit coulomb per meter cube. Now you see that the per meter squared rather, you see that in this case it already tells us that it is charge per unit area, right? This is different from the linear distribution that we saw in our previous video. So find the electric field at a point P on the axis, a distance x above the disk center. Then take r to infinity. Okay, so what is r? R is the radius. R is the radius of the disk. Okay, so let's depict this diagrammatically. So we have a circular disk. It says above the disk. So if we have a circular disk like this, so at a distance x, a point P that is on the axis, and the axis is taken from the center of the disk. So this is our point P, which is at a distance x. You know what? Let's turn it. Okay, let's turn it so that it will still be the same thing. It says this point P is above the disk. So if we turn this our disk here, the plane of our disk is going to be into and out of the board, into the board and out of the board, okay? So this will be the center of the disk, and our point P is going to lie around here, okay? So, and it's a distance x away from this center. It now says that we should find the electric field at this point, okay, due to a uniformly distributed charge on this entire disk. So in order to solve this question, the first thing we want to do is that we are going to slice up the disk, you know, into tiny rings, all right, because it's a circular disk, okay? So we're going to slice it up into circular rings, tiny rings, okay? And so let me do that here. You know, the radius of this our guy, the radius of our disk is r, okay? So by the time I cut it into smaller rings, I'm going to have one such ring around here that will have a radius. Let me make it bigger. Let me make it bigger. So if I have one of the rings that I've cut my disk into, I've sliced it up into tiny rings, okay? So this guy is going to have a radius r, right? It's a radius. Okay, let's use another letter to represent it, since we are going to define a small element of charge around these tiny rings that we have broken into, and we'll call the distance from that place to P. We're going to call it r. Remember, that is what we've been using, the notation we've been using. So because of that, I'm going to call the radius of this guy, I'm going to call it phi. So let me just, since the radius here, since it's a circular ring, the radius here is also going to be the radius here. Does that make sense? So this radius is a smaller radius than this big r. R is the radius of the big disk, okay, the entire disk from the center, and this rho, that's rho here, is the radius of the smaller ring, okay? So there are many rings here, okay? Tiny amount of rings, in maybe thousands of rings that I've chopped or sliced my disk into. I hope that is clear. Now, the next thing I want to define is that there's an angle theta here. So it means that we are moving from this center towards, so we are moving from the center where our angle is going to be 0, okay, or the radius of the rings that we are taking our small element of charge from, the radius of that ring is going to be 0 from this point until is equal to the radius of our ring, of our big ring. Does that make sense? I'm going to reiterate that. I said, since we have been given our ring, okay, our entire disk rather, our entire disk, we want to take the electric field at a point P, which is X distance away from the center of that disk. But in order to do that, what we want to do is that we want to break our disk into tiny, tiny little, our disk, we want to break into tiny rings, okay, which will start from the center. At the center, the radius of the ring will be 0. And it's going to increase. We are going to take it, infinitesimally small rings into and integrate it over the entire area of the disk. So that is our aim here. Does that make sense now? So this is going to be theta, 90 degrees rather. Okay. So what else have we not defined? Okay. So the first thing we want to do is let's define the area of this disk. Since we are given that the surface density, the charge density, surface charge density is uniform. Since the charge density is uniform, then we know that, remember that charge density, sigma in this case, okay, we are using sigma in this case. Remember in the former one, we use lambda, okay, for linear distribution. We are using different notations because there are different surfaces. Now this is a planar disk surface, okay? Now, keep in mind that we can derive this same equation using the planar symmetry of Gauss surface. The Gaussian surface symmetries or types of symmetries are, there's just there are different types of symmetries that we can use to, we can use that particular planar symmetry for Gaussian surfaces. We can use it to derive this one, okay? We have 3 symmetries, the spherical symmetry, cylindrical symmetry, and planar symmetry. But I want to show you how to use this method of charge distribution on a disk to derive that equation, okay? All right, so our charge density, sigma, is given by the quantity of charge, okay? So this quantity of charge, Q, is the total quantity of charges that have been distributed uniformly on the entire disk, okay? So divided by the area. But in this case, we are taking just the quantity of charge on our small elements of small elements defined on the ring, okay? So we are taking just this small portion of the ring, okay? Our charge distribution there, sigma, is going to be dq dA. Does that make sense? Why? Because the area of the ring is going to be dA because it's very small, okay? Keep in mind that the area of the ring can be calculated by pi r square, okay? Or the circumference of the ring times the thickness of the ring, okay? The thickness of the ring here is going to be like very small, so let's just say dr, okay? Since we said dr, our radius is rho, so let's call this d rho, okay? So that's the thickness of the ring that we have picked, okay? Now, so the charge density on this our ring is going to be what? dq dA. Does that make sense? All right. So, but let's first define the area. Since area is equal to pi r squared, and our r here for this our ring here is rho, right? So that will be pi rho squared. Does that make sense? Pi rho. Pyrolysis. All right. So it means that dA, by the time we differentiate, dA d rho is equal to, bring this guy down, that will be 2 pi rho. Okay? So that our dA will be equal to 2 pi rho d rho. Does that make sense? So this is the equation that defines our tiny little bit of area that we have taken, right? On this ring, the area of the ring. Okay? All right. So we can now substitute, let's call this equation 1 Let's call this equation 2. We can now substitute this into this equation so that our charge density will be equal to what? Our charge density will be equal to dq over dA, and dA is 2 pi rho d rho. Does that make sense now? Okay, so, and you know that our equation, since what we are looking for is the electric field at this distance here, remember that first know that there is also symmetry trick here, and the symmetry is such that every charge distribution across all the parts that are parallel to the to the plane. You know our plane is into and out of the board like this. So all the charges that are in that this thing here, they will, by symmetry, they will cancel out. So if I choose that to be y-axis, then it means that the sum of electric field will only be the ones that are due to the charges distributed in the direction that is perpendicular to the plane of my disk. Does that make sense? Okay, so if that is the case, then the E will be dE sub x alone, because only my x-axis is perpendicular to that plane, okay, to the plane of the disk. So the rest in this direction and the rest in this direction will do what? Will cancel out each other, okay, by symmetry. So E dx therefore will be equal to what? Is electric field is charge as Q over 4 pi epsilon naught R squared cos theta. So, but our Q now is dq, because we are defining it with respect to the small element we have defined here. So that will be dq over 4 pi epsilon naught R squared cos theta. Okay, since we don't have any angle here, let's define our cos theta as adjacent over hypotenuse. What's our adjacent here? That will be x over hypotenuse, which is r. That makes sense, right? So it means that our dE, since our electric field is just the one contributed by the ones on x-axis, so we'll just say E, okay? So dE, therefore, will be equal to dq over 4 pi epsilon naught r squared multiplied by x over r. Okay, so we now know that dq therefore, dE therefore becomes x dq over 4 pi epsilon naught r cubed. Okay, now you also know that using Pythagoras theorem, r squared here is going to be what? X squared plus rho squared. Okay, so if that be the case, then r will be equal to the square root of rho squared plus x squared. Does this make sense? So that we can substitute this guy into this equation. Okay, so if that be the case, then dE is equal to x dq over 4 pi epsilon naught. R is now this guy, right? So our R can be written as rho squared plus x squared all raised to the power 1 over 2, right? So we can say that into brackets r cubed becomes this all cubed. That will be rho squared plus x squared all raised to the power half, then all raised to the power 3. Okay? So if that be the case, then we know that dE will become what? X dq over 4 pi epsilon naught p squared plus, rho squared plus x squared all raised to the power 3 over 2. All right. So from here, now recall that our dq from here, let's call this equation 3. From equation 3, we know that dq from this equation, we know that dq will be equal to what? Sigma 2 pi rho times d rho. Okay? I'm using comma so that it will, but it doesn't mean if you don't put it, okay? This is multiplication that it means there, okay? So dq equals rho, yes, that's what we have here, okay? So it means that we can substitute this into the equation. Then we have dE will be equal to x sigma 2 pi rho d rho over 4 pi epsilon naught rho squared plus x squared raised to the power 3 over 2. All right. I hope you understand this. So from here, pi can take care of pi. 2 here, 1, 2 here, 2. Okay. So our equation dE becomes x sigma rho d rho over 2 epsilon naught rho squared plus x squared 3 over 2. All right. So from here we can now go on to integrate, right? So if we integrate this our function here, we'll have e will become, let's separate the constants. These two guys are constants. So that would be x sigma over 2 epsilon naught integral of rho d rho over rho squared plus x squared all raised to the power 3 over 2. Okay? So remember that we are going to be integrating. Why? We are going to be integrating from here. We are going to integrate across all the possible rings we can have here. Does that make sense? We are going to integrate across all the tiny rings that we are going to have here up until we get here. So it means we are starting from 0 to where? To r, which is the radius of the big disk. Okay? All right. So it means that our integration is a definite integral. So our integral is a definite integral. So let's, what do we do now? Let's say, since we are integrating, E equal to x sigma over 2 epsilon naught integral between 0 and r of rho d rho over rho squared plus x squared all raised to the power 3 over 2. So we'll use u substitution. Using u substitution, given the kind of question we have. So we use u substitution. What will happen? We will say that u is equal to a denominator. Okay? So that will be rho squared plus x squared. So that du d rho will be equal to what? 2 rho. This one will be 0. Okay? Then du therefore will be equal to what? 2 rho d rho. Now if you look at this here, we've been able to produce what is on top, right? From integration. You should see my video on integration in order to understand what I'm saying if you don't understand what I'm saying. So using u substitution, you will see that we have been able to have a term here so that this term, which is rho d rho, will be equal to du over 2. Does that make sense? Okay, so from there, we now know that this our expression E becomes x sigma over 2 epsilon naught integral between 0 and r of, now, rho d rho has become du over 2, right? So it means that we have 1 over, remember that this thing is u, we made it u, right? So over u all raised to the power 3 over 2. Then multiplied by this, which will now be du over 2. Does this make sense? Okay. Let's separate our integrand so that we'll not be having to rewrite all of this. So I'll keep this, I'm keeping this, so that my integrand becomes integral between 0 and r of u raised to power negative 3 over 2. Does this make sense? Dot du over 2. I can separate 1 over 2 outside, I can bring it out, so that I hope you are following. So I can clean this. Oh, it says we should take r to infinity, so don't forget. So we have to take, let me put it here, take r to infinity. So that by the time we are done, we will examine the special case of where r is at infinity. That is the size of the ring, so of the disk. So you soon discover that for an infinitely large plane body, the distance, surface charge, the electric field at any point away from it is given by the same formula. Okay, so look at this now. So I'm going to bring my integrand here. My integrand I becomes 1 over 2 integral between 0 and r of u raised to the power minus 3 over 2 du. So let's integrate this guy now. Integral of this will become, I will become integral of this. That will be 1 over 2 multiplied by u raised to the power minus 3 over 2 plus 1 over minus 3 over 2 plus 1, right? Okay, plus c. Oh no, we'll not put plus c because it's definite integral, right? So we are integrating this between r and 0, okay? So our integrand therefore becomes 1 over 2, let's clean this part. One over 2 u raised to power minus 1 over 2 over minus 1 over 2, okay? All right, so between 0 and r, okay, so I now becomes 1 over 2 multiplied by minus 2. This one will come up, right? Minus 2 u raised to power minus half. Okay? So that this takes care of this. And we're integrating between 0 and r. So that I becomes minus u. So negative means that it will become 1 over u, 1 over square root of u. So we are integrating between 0 and r. Now keep in mind that since we are integrating our row with respect to our row, we are differentiating with respect to our row. And u is equal to rho squared. U is equal to rho squared plus x squared. If this be the case, then at rho equals 0, what will happen? U will remain only x squared when rho is 0. So when rho is also r, when rho is r, comma, then u will be equal to what? R squared plus x squared. Does that make sense now? Okay, so it means that our integrand has now turned to be 1 over square root of u between x squared and r squared plus x squared. I'm just rewriting this so that we'll now start from here now. So I hope I didn't leave anything. Okay, so we can now express our integrand now so that I becomes 1 over the square root. There is a negative here. Excuse me, there's a negative here. Yes, I remember that there is a negative there because the negative will cancel a negative, okay? So minus 1 over, what will be here first? So we are subtracting the upper limit. We'll subtract the lower limit from the upper limit, right? Upper boundary. So we have square root of r squared plus x squared minus 1 over square root of x squared in this case. Does that make sense now? Okay? So that it becomes I will be equal to minus 1 over square root of r squared plus x squared plus 1 over, this takes care of this 1 over x. So we can write this, our integrand becomes 1 over x minus 1 over the square root of r squared plus x squared. So we can introduce our electric field now so that E now becomes x sigma over 2 epsilon naught of, our integrand has become this, 1 over x minus 1 over r squared, square root of 1 over r squared plus x squared. So by the time, if you open the bracket, you will have E to become sigma over 2 epsilon naught of times 1, because x will take care of x, right? Minus x times this will become x over the square root of r squared plus x squared. Now, by the time you do this, when our x is equal to 0, that is the distance between our plate, our disk, and point P, when the distance is 0, this place will be 0. Does that make sense? 0 over anything is 0, so that 1 minus 0 is 1, and this times 1 will be this. That will be E equal to sigma over 2 epsilon naught. Then it also says that we should move r to infinity. When we'll be having to move r to infinity also, we are moving r to infinity. That will be the point where x, the distance between them, okay, no. As r tends to infinity, that is as the distance between the boundary of our plate as it's increasing to infinity. You know also that one thing will happen here, that as this guy is increasing to infinity, infinity plus x squared is infinity. The square root of infinity is infinity. Anything divided by infinity is what? 0. Okay? So 1 minus 0 is also 0. So in that same case, E will also be what? Sigma over 2 epsilon naught. So I hope I've been able to prove that the electric field at an axial point on the uniformly charged disk, the electric field due to that uniformly charged disk at an axial point P on the axis of that disk is given by the formula sigma over 2 pi epsilon naught. So what does that mean? It means it does not depend on the radius of the disk, okay? And it doesn't depend on the distance away from the disk. You understand now? All right, as you can see here, okay? So I'm going to prove this in my video on electric flux and Gauss law, so that you see the way Gauss law planar symmetry shows the simplistic way of proving this, and it's cleaner, okay? Because, but you should also know how to do this so that you will know, where it's coming from. So do well to subscribe to the channel, please, and share the video. God bless you.